Stanford University.
I'll go over it again very quickly and then tell you what the Higgs phenomenon has to do with masses of quarks and leptons. So far I've explained to you how the gauge bosons, not the photon, but the Z and the W boson, how they obtain masses from this shift of the field away from the most symmetric position. Which field? The Higgs field. But I went through it in a very simple context where I made it look very much like ordinary electrodynamics, and I'll continue to do that. But keep in mind, we're not talking about the photon, we're talking about other gauge particles. So let's just go back to electrodynamics, which we're not really talking about, but still, the mathematics is the same. There are these gauge bosons, the analogs of photons. The mathematics of them may be a little more complicated. The symmetry group may not be U1, it may be SU2 or SU3, but that's not terribly important. And there is a dynamics that leads to Maxwell's equations. It's governed, in fact, as the simplest way to encapsulate it is in terms of a Lagrangian. You begin with a good pen. You begin with the field tensor. Let me just remind you what it is. It's in terms of the vector potential. You begin with that. You square it. Let's just call it F squared. You make the appropriate Lorentz invariant combination of squares of components of electric and magnetic field. And that's the Lagrangian. And notice it only contains derivatives of A, and therefore the photon is massless. To have a mass, you have to get an energy. A mass corresponds to an energy corresponding to shifting a field homogeneously everywhere with no derivatives. This has no energy or no energy associated with a uniform shift of the vector potential because only the derivatives come in. And so the photon, by virtue of this, is massless. It moves with the speed of light. And this simply leads to Maxwell's equations. Now you add something else. You add this Higgs field. The Higgs field is a field which corresponds to charged particles. Again, I emphasize we're not talking about ordinary electric charge. We're talking about the charges that couple to the Z and W bosons, the weak charges. And we write this phi in the form rho e to the I alpha. It's a complex valued field, rho times e to the I alpha. And we write down its Lagrangian. We write its Lagrangian in terms of these things that I called covariant derivatives. D phi is equal to the derivative of phi plus, or I can't remember if it's plus or minus, I times the vector potential times phi. We write the Lagrangian in terms of those things. And all of a sudden, we have an interesting interaction between the electromagnetic field and the charged field. Here's the source of the interaction right over here. That would be, basically that would be electrodynamics, ordinary electrodynamics. But now something new happens. The something new that happens is the energetics, the potential energy of phi, favor something unusual, namely that phi is the minimum value of phi, the minimum value of the potential energy is not at phi equals 0, but at the bottom of this Mexican hat potential somewhere, an arbitrary position along there. And so we write that phi, let's say the radius of this circle here is f. The magnitude of the field, the magnitude of this, let's call it by its name, the magnitude of this Higgs field is now f. It's shifted away from the origin by amount f. And it is also true that the curvature at the bottom here is very steep. And so it costs a lot of energy to shift the field away from the bottom here. In some first approximation, we can just say that phi is simply equal to f, the numerical number, times e to the I alpha of x. Only alpha is allowed to vary, and f is sort of frozen. Frozen because it takes too much energy to shift it away from the minimum, but alpha, the angular variable, is still there. All right, we could write, let me tell you what happens now. We could take this form for phi and figure out what the covariant derivative of phi is, given that phi has this frozen form where only alpha varies. I'll write it for you. It's just equal to the derivative of alpha plus IA. Now, all of that gets multiplied by f times e to the I alpha. That's the covariant derivative of phi. The derivative of alpha, sorry, I think it's I, no I here, plus this, and maybe there's an overall, yes, I think there's an overall I. That's what you get when you calculate the covariant derivative. Now, next thing we're going to do is multiply this by its complex conjugate to compute the action, or the Lagrangian, for what? For f? No, f is just a number. We've already assumed that f can't vary very much. The Lagrangian for alpha. Now, let's see what we get. We're going to get f squared, the number f squared, that's a number. And then we're going to get derivative of alpha, that's the derivative of alpha with respect to space or time, plus the vector potential squared. And e to the I alpha is going to cancel because we're multiplying it by its complex conjugate. This is what you get for the Lagrangian of the Higgs field if you make the approximation that it's stuck, where is it? That it's stuck and can't move away from the minimum. I may have blown the sign, but did I blow the sign? I don't think so, but. No, there was also an I in this term because when you differentiate phi, you'll get I times the derivative of alpha. All right, so both of them have an I, and I stuck it out over here.
No, I mean in the dp star.
Oh, yeah. Let's see. Yeah, I times minus I is 1.
Okay.
Yeah, I times minus I. You scared me for a minute. Well, it's not I squared, it's I times minus I.
Well, it just wasn't written, so I wasn't quite sure what to think.
Well, the complex conjugate involves minus I. Okay. So what do we get? We get this expression over here. Now, do you remember what a gauge transformation looks like? Gauge transformation, which is a symmetry, which is supposed to do nothing to the physics. Take any function. Let's call it theta, which is what I called it last time, but it could be anything. It could be anything. A gauge transformation is to take A and shift it by the derivative of theta. That's a gauge transformation. Okay. But look at this. This is A plus the derivative of something. This is a gauge transformation. This is a gauge transformation where what we have used for the gauge transformation is not an arbitrary function theta, but this alpha field itself. Now look what we have. Let's redefine A plus the derivative of alpha. It's just a gauge transformation of A. Let's redefine it. Let's give it a new name. Let's call it A prime, okay? Let's call it A prime. This is f squared times A prime squared. That's all this is. What happens to f squared, which originally involved A? What happens to f if we replace A by A prime? It's completely unchanged because f is gauge invariant. And so we can also think of F squared, or F, there's this thing over here, doesn't make any difference. And what do we find? That the net upshot of it all is to just replace the original variables by prime variables, and that's just renaming, that's just a new name for something, and to add a term in the Lagrangian which is proportional to the square of the vector potential. That was the net effect. Just add a term to the Lagrangian for the gauge field, which is proportional to a squared. No derivatives in it. There's no derivatives in this term here. It's just a prime squared. That means that if you were to shift a prime everywheres simultaneously, you would get some energy from this term. This term is a mass for the photon. It's not the photon, of course, it's the Z and the W boson. So here's an example of how this shift of the field from 0 to value F gives a mass to a particle which you might have said is not allowed to have a mass. How did it happen? The vacuum shifted to some new spontaneously broken vacuum, and the excitations of the electromagnetic field in that shifted vacuum have a mass. Okay, so that's the Higgs phenomena. And furthermore, the alpha field is gone. It's gone. It's been absorbed into this thing we called A prime. So there's no massless particle anymore. The Goldstone boson has disappeared. It has made a mass for the gauge boson. And that's it. Now, not quite it. There is still this thing that we froze in an approximation. In an approximation, we said, let's ignore the oscillations of the field back and forth in this other direction. If we're giving the system enough energy, if we really poke it hard enough, we can start this Higgs field oscillating in the radial direction. Let's call it the radial direction. It's not a radial direction in space. It's this radial direction in field space. Those oscillations also are quanta. And they're massive quanta. Why? They have a lot of energy even at rest. They oscillate back and forth. And those are the Higgs bosons. Those are the Higgs bosons. So we started with massless photons, massless Goldstone bosons, and massive Higgs bosons. And we ended up with massive Higgs bosons, no Goldstone boson, and a massive photon. That's the Higgs phenomenon. Okay? All right.
Could you say again why the A prime squared indicates a massive?
Yeah, whenever you have a, all right, first of all, what is a mass? A mass is an energy, from a field theory point of view. Mass, of course, is inertia of a particle or whatever. But from a field theory, well, let's go back a step. A mass in special relativity is just the energy of a system at rest. If a system has no momentum, if it's at rest in its own reference frame, then the energy in that reference frame is the mass. So that's the first step. Energy at rest is called mass. Now, what does being at rest mean? Being at rest means having no momentum. From a field theory point of view, from the point of view of fields, or from the point of view of quantum mechanics, a particle at rest or a particle with zero momentum corresponds to the quantum of a field of infinite wavelength. Infinite wavelength means the field doesn't vary at all from point to point. And so a mass, what it corresponds to, is an energy stored in a field if you shift the field simultaneously everywheres. With no derivative, no spatial derivative, just shift the field everywhere simultaneously. If you get some energy, that energy is called the mass. Okay? Well, we started with a Lagrangian and also an expression for energy which only involves derivatives of a field. If it only involves derivatives of a field, it means that if we shift the field everywhere simultaneously, we won't get any energy. So in that sense, if this was all that there was for the photon, then we would say the photon has no mass. A uniform shift of the vector potential would not create any energy. We say the photon has no mass. But now, once there's a term in here like this, which doesn't involve derivatives, does not involve the derivatives of A, that means if we shift A simultaneously everywhere, the response, the energy stored in this term, is not zero. We shifted A from 0, where the energy was 0, to something else, so we got some energy. That energy is called the mass of the photon. So it's energy stored in, does everybody know what I mean by homogeneous? Homogeneous means everywhere is the same, all right? If you shift the photon field, everywhere is the same, and you get any energy from it, that's the mass of the photon. In fact, in particle physics or in field theory in general, you identify the mass of a particle as an energy stored in shifting the field simultaneously everywhere. Okay. It's not just in particle physics, in all kinds of contexts. I think I talked about them last time, but let me just remind you again. A sound wave in a crystal. A sound wave in a crystal corresponds to a motion of the crystal lattice, which you could think of as the response to a shift of the position of the molecules. If you shift the position of the molecules in a variable way, in other words, way down here, you shift them to the left a centimeter. And then halfway down there, you shift them to the left a half a centimeter. And then over here, you don't shift them at all. And then over here, a half a centimeter to the right, and so forth. You make a long wavelength, it's called a phonon, a long wavelength phonon, but it's a kind of wave in the crystal where we're very slowly varying. And there's energy stored in that. You've deformed the crystal a little bit. That energy is called the energy of a phonon. Now, what happens if you shift the crystal everywhere simultaneously by exactly the same amount? We could call that a homogeneous shift. Do we get any energy from that? No. So a homogeneous shift where everything is shifted simultaneously all together, that gives no energy. And so you would say phonons are massless. Phonons have no mass, which means that a phonon with 0 momentum has no energy. Phonons, photons, spin-ons. Spin-ons are in magnets. They have to do with the orientation of the little fundamental magnets. If you reorient the magnets in a variable way from place to place, you get a little bit of energy. It's called a spin wave. If you rotate all the magnets together simultaneously everywhere, it costs no energy. You just rotated the magnet. So that's another example of waves which at infinite wavelength or homogeneous waves have no energy. They're also massless.
I thought we started out this analysis with a particle that was vibrating a little bit in alpha.
Yeah,
And
we did.
now,
And that originally, before we coupled it to A, to the vector potential, its energy was purely rho squared d, well, it's just, let's call it f squared d alpha squared. That's all there was. It was just the square of this thing where the vector potential was completely absent from the problem. Okay? Now, because it only involves derivatives, if we shift alpha everywhere simultaneously, in other words, everywhere in space, we shift the angle, instead of saying the field has the value over here, we put it over here. Everywhere in space. That costs no energy. It costs no energy because it didn't make any derivatives. I'm not sure what the question was, but does that answer it?
well, by shifting it, you're changing alpha,
You're changing alpha.
and that means,
But it's derivatives of alpha which give you energy.
oh, because you're not continuously moving it in alpha. Is that-
That's right. You're not moving it. You're not changing it from place to place. If you change it from place to place, that's the energy of the Goldstone boson. All right? But if you shift it everywhere simultaneously, then it costs no energy. Why? Because the energy only involves gradients. Okay? So That's the idea. So keep that in mind. That's a buzzword. That mass stands for energy at rest, but it also stands for energy associated with uniform, homogeneous shifts of fields or whatever it is we're talking about. There is an interesting example to get an idea of how mass can happen. I explained to you that if you have a crystal and you move all the molecules simultaneously, it doesn't cost any energy. Now, supposing your crystal lattice was composed of particles which themselves had both some plus charges and some minus charges. Okay? So these are molecules or ions, plus ions and minus ions. Or it could just be atoms. They could be the protons at the nuclei at the center and the electrons around them. And supposing you did the following. You shifted all of the electrons to the left uniformly and all the protons to the right uniformly. That would be called a homogeneous shift. Just a little bit, just a little separation between the electron cloud and the nuclei. Do you think that would cost any energy? You bet, because you would have pulled the plus charges away from the minus charges. That would be a homogeneous shift of not fields, but locations, which would cost energy. What do you think would happen if you made that shift, the plus particles this way, the minus particles this way? What will happen next? It'll start to vibrate, okay? It will not behave the way it would if everything was moved simultaneously. So moving everything simultaneously, that's a zero momentum phonon. Moving the plus charges relative to the minus charges, what is that called? Anybody know? A plasmon. A plasmon. Plasmons have mass. Phonons do not. Okay?
The derivatives there include a time component, don't they?
The derivatives include what?
A time component.
Oh, yeah, absolutely.
So
Absolutely.
when you're talking about shifting things, doesn't the time component?
Yes, what you're saying is right, but I'm just imagining spatially shifting everything and not inducing any time derivatives. Well, all right, good. No, it's a good question. No. By shifting, I don't mean an actual process. I just mean a mathematical change in what you mean by the vacuum. Right. Or you do it extremely slowly, very, very slowly, move it from here to here. Yes, you're right. The actual energy contains time derivatives also, but I was simply, the same is true incidentally of the crystal lattice. What are the time derivatives of the shifts? The kinetic energy, the velocities of the molecules. So if you really give the crystal a shift, which means it's moving off with a velocity, then of course there's kinetic energy. So when I said a shift, I meant a shift in your imagination where you shift everything simultaneously and started out at rest compared to where originally was also at rest. Good. But that's a good point. Okay, let's talk now about fermions. This means electrons, muons, and so forth, and where they get their mass from. It turns out the real electron, muon, quarks also get their mass from this Higgs phenomenon, from this spontaneous symmetry breaking. And let's discuss what we know about it. The first thing we go back to is the basics of the theory, not the theory, but actual experimental data about weak interactions. This could be beta decay, the decay of a neutron to a proton, but and an electron and an antineutrino. Okay, here's what goes back to the 50s? The 50s. No, earlier than the 50s, I think. I don't remember exactly when. The following fact was discovered. First of all, reflection symmetry which means reflection of space, left hand into right hand, is not a good symmetry of nature. It's an ancient fact from the 50s that it was discovered that the reflection, the mirror reflection of a process is not another possible process. Now, in quantum electrodynamics, the mirror image of any process is another possible process. That itself is a symmetry. It's not a continuous symmetry, it's a discrete symmetry. You take everything and you reflect it. You don't rotate it, you reflect it. You take the left hand and the right hand. There's no hand which is sort of midway, there's no continuous way to go from left hand to right hand. So replacing every left hand by a right hand, or every left screw thread with a right screw thread and so forth, that's a symmetry of quantum electrodynamics, and it's also a symmetry of quantum chromodynamics. It is not a symmetry of the weak interactions. Left and right are fundamentally different, and as different as they can be. So let me tell you what the experimental fact is, that the decay of a neutron, which gives a proton, an electron, and an antineutrino. Well, let's first talk about the handedness of particles. Is there any sense in which particles are handed, have a handedness, like my hands? Yes, there is. They have a spin. They also have a direction of motion. All right? If the spin is along the direction of motion, in other words, there are two possibilities. The spin can be oriented along the direction of motion, or it can be oriented opposite to the direction of motion. In quantum mechanics, of course, if the spin is oriented in some other direction, you can build it up out of superpositions of the two states along the direction of motion and opposite. All right. So an electron moving along with a high momentum, for example, can either have its spin along the direction of motion. That means it's rotating with a right-hand screw thread. Okay? It's rotating or spinning with a right-hand screw thread. That's called a right-handed electron. And an electron can also be a left-handed electron. That simply means its spin is going, is helically going in the opposite direction. So there are two kinds of electrons, right-handed and left-handed. Okay. Now, what happens in a beta decay like this? You might think you could either make right-handed or left-handed electrons. Right-handed and left-handed electrons are as good as each other in every respect. In quantum electrodynamics, there are no processes which are not symmetric. If you can make a right-handed electron in some process, then there's a reflected process, which is also a possible process where you can make a left-handed electron. If right is possible, left is possible. Nevertheless, when the process of beta decay became something where you could really do with precision and study the handedness of the electrons that come out, they're always left-handed. There is never a process, it doesn't matter what orientation the spin of the neutron has, no matter what you do, the electrons which come out are always left-handed. This goes beyond the theory of beta decay, any weak interaction process. In other words, any process where a W boson, for example, where a W boson interacts and takes an electron into a neutrino, or where you interchange, where you flip these lines to make different processes out of it, it's always the left-handed electron which interacts with the W boson, never a right-handed electron. Okay. So for example, you could imagine a process where an electron scatters off something, changes into a neutrino, and there's something over here that it scatters off, a proton or something else or another electron. You'll always find that the left-handed electron scatters and the right-handed electron doesn't. This is a fact. And the same thing is true of the neutrino, incidentally. It's always a left-handed neutrino. It's questionable whether a right-handed neutrino exists, incidentally. This is a question which we've not answered. We'll come back to it another time. But there certainly exist both right-handed and left-handed electrons. We think there are also probably right-handed and left-handed neutrinos. All right, so electrons, so there's something asymmetric, left-right asymmetric about the weak interactions. And it is, what is it? It is that the left-handed electrons are charged with respect to the W boson. In other words, we could imagine a situation in electrodynamics which would be similar. It's an untrue situation. Let me say right now, this is not correct. All right? But we could imagine a world in which only left-handed electrons are charged. Left-handed electrons could scatter off photons or could produce photons and become left-handed electrons, and in which right-handed electrons could not. We could imagine it. It's not true. We say it over and over. It is not true, but imagine it. Then you would say that the left-handed electron has an electric charge and the right-handed electron does not. Now that's bizarre. I mean, that's really bizarre. Okay? And it's not true. But with respect to the weak interactions, not the emission of a photon, but the emission of a W boson, it is as if the left-handed particles carried charge associated with the emission of a gauge boson, and the right-handed particles did not. That's a very strange fact. It's an empirical fact. What's that? It's also true of quarks. It is also true of quarks. We're going to modify the statement a little bit, but at some deep level, it's exactly true. Okay, let's talk about left-handed and right-handed particles, fermions. And let's go back to the Dirac equation. And I will tell you a little bit about the connection between the Dirac equation and the handedness of particles. I'm not going to spend a lot of time. I'm just going to give you the rough outlines of the idea. Let's go back to the Dirac equation. The Dirac equation looked something like this. I d psi by dt. This is the Dirac field, which could correspond to the electron. It could correspond to the muon. It could be the field for quarks. They all have the same form, the Dirac equations. The time derivative of the Dirac field, and remember what the Dirac field is it's a four-component object where the four components correspond to, let's say, two different subdivisions. The particles can have spin along either axis. That gives you two components, upspin and downspin. And the particles can have positive or negative energy. Remember, Dirac particles can have positive or negative energy. Now, we've learned over and over again that the negative energy particles should be replaced by antiparticles of positive energy. But in the mathematics, the Dirac field has four components: upspin positive energy, downspin positive energy, upspin negative energy, downspin positive energy. Or you can think of it as upspin and downspin of particle and antiparticle. Okay, so there are four components to the Dirac field, and the components, think of it as a four-component column vector. There are matrices, 4x4 matrices called the Dirac matrices. Dirac called them alpha. Three alphas, one for each direction of space. Let's call them alpha I for the three directions of space, times the derivative of the field with respect to x sub I. This would be the Dirac equation if the particle had no mass. Now, how can you see that? You can see that because the equation only involves derivatives of the field. If the field, the whole dynamics of the field only involves derivatives of the field. We've seen in previous situations that when the dynamics of the field only involves derivatives, the field is massless. There's no restoring force, no tendency for the field to oscillate unless it has a gradient. No time derivative unless there's a space derivative. So if you shift the field psi everywhere simultaneously, it does not create an oscillation, does not create any energy. All right. What do you put on the right-hand side if you want to have a mass for the field? Well, there was a fourth Dirac matrix called beta. You put the mass times beta times psi. That's the Dirac equation. Now, the electron could be moving along with a momentum. A momentum means there's a gradient of the field psi. It means a plane wave, but that's not so important. And the spin can either be along the direction of motion or opposite to the direction of motion. Those two components, we can think of that as the left-handed components of the Dirac field and the right-handed components. So let me write these equations for you. This is 4 equations, one for each component. Let's write them for the left and right-handed components separately. Here's what it looks like. I times the derivative of the right-handed component of the Dirac field, describing right-handed electrons, plus I alpha I derivative of the right-handed field is equal. Now you might think that the right thing to put here is something involving the right-handed field. But it turns out this matrix beta interchanges right hand and left hand. So a mass term over here corresponds to a coupling between right-handed and left-handed. And likewise, here's the equation for the left-handed component. d psi left-handed by dt. Turns out it's minus I alpha sub I d psi left-handed by dxi is equal to m psi right-handed. In other words, it's a funny equation in which the right-handed and the left-handed components are completely independent if the mass is 0, but the mass mixes them up. Roughly speaking, you can think of a Dirac electron as one which, as it moves along, oscillates between left and right. And the oscillation is the mass term. But let's not push that too hard. It's not quite right. The mass term couples together the left-handed and right-handed components. This is, for a Dirac particle, what a mass term is. It's a thing which couples together. It's an energy which is only there if both the left-handed and the right-handed components are both excited. Okay, now we can see what some odd things. Let's suppose that only the left-handed Dirac particle had a charge, which is true with respect to the weak interactions, not true with respect to the electromagnetic, but let's just pretend. Only the left-handed electron has a charge, the right-handed electron has no charge. Okay? A fictitious world. Is this equation allowable then? Well, it's not, because the meaning of this equation is that a right-handed particle moving along will turn into a left-handed particle. I'll explain it another way in a second. And a left-handed particle moving along will turn into a right-handed particle. What does this mean? It means that charge conservation would be violated. A right-handed field becoming a left-handed field would violate charge conservation. Another way to say it is to remember that a charged field, if a field has charge, it gets multiplied under a gauge transformation or under one of these U1 transformations. It gets multiplied by e to the I theta. If it has no charge, it does not get multiplied by e to the I theta. Now we look at this equation. This equation, if the right-handed field is neutral, has no charge, then under a U1 transformation, nothing would happen to the left-hand side, but the right-hand side would pick up a factor of e to the I theta. Likewise over here, the left-hand side would pick up a factor of e to the I theta, the right-hand side would not. These equations cannot be symmetric if only psi left is multiplied by e to the I theta and not psi right. That's another way of saying that charge conservation would not permit a mixing of left and right like this if only the left-handed electron were charged. Both of them are charged in reality, and because both of them carry the same charge, you can go back and forth from left to right without violating charge conservation. Yeah?
I wonder if the eyes on alphas are consistent?
Probably not. No, they're probably not. Oh, no, I meant sorry. No, you're right, they're not consistent. I pulled the whole eye out on the outside. You're right. Okay. Yeah. Okay. So it's just basic charge conservation would forbid the possibility of a mass for the electron if only left-handed electrons had charge, or if only right-handed electrons had charge. Fortunately for the real world, that's not true. Electrons, both right-handed and left-handed, have charge. The electron has a mass. The world would be very different if the electron didn't have a mass. And chemistry wouldn't exist. Yeah, we wouldn't be in a happy world.
How would the world be different if right-handed electrons could be emitted from weak interaction as well as left-handed?
If both right-handed and left-handed. We'll come to it. We'll come to it. It would be very different, but we will come to it. Okay, so let's come to the weak interactions. Yeah.
A question, you can measure the spin of electron vertically unless they select the ones that are pointing upward. And if you accelerate those in that direction, do you say they have a spin as the type that you're talking here? The same thing? Mm-hmm. Okay, thank you.
There's an interesting question. Is it possible that there would only be one kind of electron, namely only left-handed electrons? Okay. Yes, it is, but only if they're massless. So let me explain why. Supposing there was only a left-handed electron, that means it spins only to the left when it moves. You know, it has a left-handed helical kind of motion. All right? Now, if the electron has a mass, you could imagine slowing it down and bringing it to rest. Bringing it to rest in a way that doesn't change its angular momentum. You could exert a force on it which doesn't change its angular momentum. So in that case, you would take this electron, which is moving along, rotating to the left with a left-handed motion, bring it to rest, and even go past that, bring it back the other way. Its rotation, sense of rotation hasn't changed. That's just angular momentum conservation. But its direction of velocity has changed. It has turned into a right-handed electron. Right? If I judge by my thumb. If it's moving in that direction, then the direction of my fingers is its handedness. Right? So if it's rotating that way and moving that way, it's left-handed. But if it's rotating that way and moving that way, it's right-handed. So if the particle has a mass, you can always bring it to rest and over-decelerate it and send it off in the opposite direction, and you're guaranteed then that you've taken a left-handed electron and turned it into right-handed. Okay, if it has a mass. What if it has no mass? Then you simply can't bring it to rest. You simply cannot do this process of taking it, moving in that direction, slowing it down, bring it to rest. What you can do is rotate it around but that does not change. I don't change my left hand to my right hand when I rotate around. But if I can bring it to rest, then you can be sure that both kinds have to, if I can bring it to rest, I can be sure that both kinds necessarily have to exist. You can only bring an object to rest if it has a mass. So there's another way of thinking about, yeah.
What happens to the photon in the outside there? Photon coming in that top.
A circularly polarized photon. Okay, it changes its polarization. If it's rotating that way and it bounces off the mirror, it will continue to rotate that way, but it will go in the opposite direction. That means it's changed from circular polarization right-handed to circular polarization left-handed. So the photon is also...
But it never came to rest, right?
well, that's right. It never came to rest. Right. Right. Okay. If you had a particle which only could have one helicity, helicity means this handedness, then you couldn't have a mirror that reflected it. Right. That's a good point.
If you have an electron beam,
Yeah.
you have all the electron in one spin or both spins?
Well, generally you have both. But because real electrons have a mass, it means the electron, the real electron, is a mixture of both kinds of handedness.
So then what do you do to focus?
Why would it be difficult to focus it?
Because the spin is different.
No, that doesn't make it hard to focus then. Focusing doesn't have to do with their spin, it has to do with their positioning.
Yeah, focus is done because it makes length. So the spin changes.
I'm not sure what the point is. Say it again.
You will focus on two different spots.
The left-handed and the right-handed. It could happen. It depends on exactly what's focusing it. Now, to a good approximation, left-handed and right-handed particles in an electric or a magnetic field behave the same way. They have the same trajectories. Not quite, because of the difference of the magnetic moment. Right? So magnetic moments are small of an electron. And if you have a gradient of an electric field or a gradient of a magnetic field, a magnetic field in general, I think what you're saying is a magnetic field will affect the left-handed and the right-handed electrons differently. Yeah, this is true.
So you have double.
Yeah, that's right. That will happen. That can happen. Right. Okay. So here we are. We're in a world of.
Does this fact that left-handed and right-handed are different, is that just an accident of nature, or is that?
Does it what?
Is that just an accident of nature, or is that?
Probably not an accident of nature. It's not an accident of nature, but for the moment, let's treat it as an accident of nature, an empirical fact that we know for the moment. Okay. All right. If it's true that the mathematical Dirac equation, if the left-handed particle and the right-handed particle have different charge, then the Dirac equation or the symmetry of the system will not allow us to mix right-handed and left-handed like that. Then the question is, how might the electron get a charge, or get a mass, excuse me. How might it get a mass in this fake world in which left-handed and right-handed electrons have different electric charge? I use electric charge just because it's familiar, and I want to make this, but it's really the weak interaction forces that we're interested in. All right, let's imagine that there's another field. Let's make it a boson field. A boson field phi. And this boson field phi is also charged. Let's say it has plus charge. Boson field means its quanta have positive charge. Let's write down the rules of transformation under these U1 symmetries. First of all let's write them over here. Under a U1 transformation, psi left goes to e to the I theta psi left, Why? Because left-handed electrons are charged. What happens to psi right? Somebody yell out. It just goes to psi right. It doesn't transform at all. And what happens to phi? It's charged, right? It's charged by assumption, depending on the sign of the charge. Let's say it goes the same way as this one, e to the I theta phi. Okay, now let's come back to the Dirac equation over here. Clearly, the equation as it stands is not invariant under this operation. The left-hand side of the top equation does not transform. The right-hand side does transform. Same thing with the lower equation, except opposite. But now let's play a trick. Let's take this mass, throw the mass out for the moment, and put in here a constant, some unknown constant, which we'll fix later, a numerical constant, times phi, let's see, the left-handed one transforms, times phi star, and this one times phi. Is this legal now? This one doesn't transform at all, right? What about this? Psi left gets a phase, but phi gets, or phi star gets the opposite phase. So we haven't violated the symmetry, the U1 symmetry. How about this one? No what? No, it's good or no, it's bad? No, it is good. Let's see. Psi right does not transform at all, and I think psi left and phi transform the same way, right? So phi right doesn't transform at all. Psi left picks up the factor of e to the I theta, but so does phi. So both of these equations are now consistent with the symmetry. This is a perfectly good alteration of the Dirac equation, which does not violate charge conservation. There's another way to think about it. You can think about this picture as saying a right-handed, the left-hand side represents the propagation of a right-handed particle, and the right-hand side represents the splitting into a left-handed particle, and I guess it's a phi particle, phi or opposite, an anti-phi particle. So a neutral particle breaks up into a left-handed particle which has charge and a right-handed particle which has the opposite charge. That's what this equation means. Particle propagating along makes a transition to two particles. One is left-handed and one is of the phi star type. Conserves charge, and so you can say the same about this one over here. A left-handed particle moves along and becomes a phi, and a right-handed particle. That also conserves charge. So that's the way you can think about this. It just describes a new kind of process in which lefts and rights can turn into each other, but only at the cost of emitting charged particles to compensate the charge. What's the probability for emitting such a particle? What's the strength of this interaction? It's this constant G. The G is called a coupling constant. It's not the electromagnetic charge. It's none of the coupling constants we've already described. It's called a Yukawa coupling. All right, now let's come back to phi. Let's suppose phi is one of these magical Higgs fields. Supposing phi is one of these magical Higgs fields, remember the Higgs field is also a charge-carrying field, and let's suppose it has the form rho e to the I alpha. In addition, something which is definitely not true of electrodynamics, let's suppose this phi field has gives rise to a spontaneous symmetry breaking, so that in fact it has magnitude F. Let's forget alpha for the moment. Remember alpha, what happened to alpha? It got eaten by the Higgs phenomena and disappeared out of the system. But rho itself or phi was just proportional to this F quantity. What was F? F was just the shift of the field away from the origin. Then what happens over here? Right. Phi is too rigid to get excited very easily, and so it's just approximated by a constant. This just becomes approximately G F psi left. This becomes approximately G F psi right.
How do you separate G from F?
G is just a number. So is F.
So they can't be separated, really.
Well, okay, here's how we separate them. We go back, remember what happened to the photon in this fake world? It got a mass equal to F. So we look at the photon and we say the photon, not the real photon, I really mean the Z and the W. We look at the Z and the W, and that tells us what F is. Then we look at the fermions, and we see what G is. All right? But what is this combination? This combination is playing exactly the same role as the original mass in the Dirac equation. So another magical example of how a shift in the Higgs field gives rise to masses for particles. The masses for particles simply meaning the coupling between left and right-handed. Left goes to right-handed. We identify that as the mass of a fermion. And here we see that it can happen, but only if the symmetry is spontaneously broken. Okay? So the Higgs phenomena has another role. It gives the fermions mass. How big is the mass of the fermions? The mass of a fermion is equal to some G times F. Now, there are different fermions in our world. There's the electron, there's the muon, there are the various quarks. That only means that there are a collection of different G's in the world. These G's are called Yukawa couplings, and there's one for each kind of fermion. There's an electron Yukawa coupling. Let's estimate, how big is the electron Yukawa coupling? Remember that the mass of the Z boson, or the W boson, is essentially F. Anybody know what the mass of a W boson is? It's about 900 GeV, right? Did somebody say? How much? 90? Sorry, 90 GeV, not 900, thank you. 90 roughly 100 GeV. What's the mass of an electron? So we could be talking about electrons here. This would be the Yukawa coupling for the electron. Half an MeV, right? So G electron here must be a very small number. What is it? It's the ratio of the electron mass to the Z mass, and that's 100 GeV versus half an MeV. That's 1,000, a big number, hundreds of thousands. How much? 200 what? That's 100 GeV versus a half an MeV. Okay? The difference between an MeV and a GeV is a factor of 1,000, so it's roughly a factor of 10 to, this number is about 10 to the minus 5. Very, very small number. How do we know it? We know it from knowing both the mass of the W boson and the mass of the electron. Next, what's the next one? The next one is the muon, or the up quark, or the down quark, and there's a variety of different numbers. What's the heaviest of the quarks? The top quark, and what is that? How much? What's its mass? It's about a factor of 1.5 or 2 times, somewhere between 1.5 and 2 times times the mass of the W. So that means for the top quark, this number here is a number of order 1. Right? So there's a whole spectrum of these different Yukawa couplings that nobody understands. Right? But one thing that's interesting is you say, so, okay, so all you've done is fit a collection of numbers to the masses of the fermions. But now you can hope for an experimental experimental confirmation of these numbers. Let's go back to the coupling of the right-handed and the left-handed particles here. And remember that F was simply the frozen value of the Higgs field. But the Higgs field is not really frozen. It really can shift around. What is the Higgs field? The Higgs field is the fluctuation away from this frozen value, the real Higgs particle. The real Higgs particle is the fluctuation away from here. So in fact, what we should really write, if we're doing it correctly, is write F plus the Higgs field times psi left. What is this telling us? This is telling us that, sorry, this right? This is right, I think. No, left? Yeah, left. This is telling us that a process can happen where a right-handed fermion can turn into a left-handed fermion and a Higgs particle, a real process. Right-handed particle can become a left-handed particle and a Higgs particle. And what's the amplitude for that? The same Yukawa coupling.
What is that word before coupling?
Yukawa. Yukawa was a Japanese physicist. Sorry. Yukawa. Yukawa. Yukawa was a Japanese physicist in the 40s who, among other things, wrote down the mathematics of the couplings between fermions and bosons like this. Right. Won the Nobel Prize for this in the 1940s for different physics, for nuclear physics applications of these ideas. But in any case, the point is that the same coupling constant, which appears in the mass of the fermions, also governs the process of a fermion becoming a Higgs boson and another fermion. I should draw these as solid lines. Fermion left-handed becomes fermion right-handed and a Higgs boson. Now, we've not detected the Higgs bosons yet. We've not detected them yet. So it becomes a very, very important thing once the Higgs boson is detected to study the different processes in which Higgs bosons are produced to see that the relative probabilities of producing a Higgs boson by an electron and by a top quark or another kind of quark, that they have the same ratios as these constants here. For example, it tells us that in the decay of the Higgs boson, this could be read as the decay of a Higgs boson into a pair of fermions, that it prefers to decay into the heaviest fermions. If it has enough energy to do so, it will preferentially decay to heavier fermions rather than light fermions, and that's a consequence of this because the couplings here are larger. So that's one of the things that will become important in the LHC, is to study the properties of Higgs bosons and see if we can detect evidence for these coupling constants. Yeah.
So basically all the coupling constants, regardless of where they come in, are really probability numbers.
They're square roots of probabilities, if you like. Yeah. Sometimes they're fourth roots of probabilities. You know, it depends on how many times you have to square, but yeah. Right. They're related to probabilities, and
so there's an assumption here that there's only one such Higgs boson that everything couples?
I have made the assumption that there's only one type of Higgs bosons. In various more complicated theories beyond the standard model, there are often more than one. And then much of what I have to say, for example, there are Higgs bosons, well, yeah, there are in the supersymmetric models, there are usually two Higgs bosons, but then you just modify it accordingly. And of course, much of what I say has to be modified because the weak interactions are SU2, not U1. So what I'm doing is giving you a kind of simplified version of what the Higgs phenomena does. But thus far, taking into account all of the various gauge interactions, here's an interesting fact. All of the particles that are seen in the standard model could not have a mass if it were not for this shift. for this shift of the Higgs field. The gauge bosons, they normally do not have mass. And the only way to give them the mass, the only known way to give them mass, is this phenomenon of spontaneous symmetry breaking associated with the Higgs field. Their mass is typically proportional just to this F. Right? So the Z and W boson. All of the fermions, because of this peculiar property that the weak interactions are purely left-handed, the symmetries of the gauge theories do not allow you to just write down, in other words, to postulate a mathematical mass term for these fermions. The only way that they get mass is through this shift of the field. To say it yet another way, all of the masses of the known particles are such that they are proportional to this symmetry breaking parameter, F, the shift of the Higgs field. That's a curiosity which may be deep, it may be important. Yeah.
Question, if you have antiparticles and they decay, beta decay, would the direction be the opposite?
Yes.
Okay.
Yeah, that's a good point. If an electron is purely left-handed, then its antiparticle is purely right-handed. Yeah. But nevertheless, we continue to call it left-handed. We call it, we still say the electron is left-handed. Yeah.
You say left-handed anti-electron or positron?
The positron would be right-handed. The positron which interacts with the Z and W boson is right-handed.
So you call it by its hand?
You call it
by its handedness, not by the handedness of its antiparticle?
It's just a pure convention. We have a lot more experience with electrons than we do with positrons, so we tend to name things by we tend to say the electron, meaning the full complex of objects that go together with the electron are called left-handed. Nevertheless, the positron is right-handed.
So what do we collide the electrons and positrons? What do we do about their spin?
Well, an electron and a positron, if collided together, can make, for example, a Z boson. So I guess it would be a left-handed electron and a right-handed positron could make a Z boson.
Are all positrons created by the Higgs decay?
No, you can create positrons in all kinds of ways. You hit any particle hard enough with anything, and it will make, among other things, positrons. Right. Certainly not all positrons in nature are made of... For example, you can make positrons by just colliding an electron with a photon. You hit an electron hard enough with a photon, and you'll make the electron won't disappear, but out will come an extra electron and a positron. Okay, for example, let's see if we can work out the Feynman diagram that describes that. Okay, so the Feynman diagrams, the basic Feynman diagram, or the basic vertex, is electron, electron, and photon. But if we flip the lines around, we can turn this into electron, let's call this E minus, E plus, that's positron, and photon. Or, better yet, let's see, so what did I say? We said electron collides with a photon and makes an extra electron and positron. Okay, so here's the photon colliding with the electron. Then another photon emitted, and that photon turning into an electron and a positron. All right, so that's a Feynman diagram, a fairly complicated Feynman diagram that would take an electron and a photon and turn it into an electron, two electrons, and a positron. So there's all kinds of processes that can make positrons.
On the Nina accelerator, can you select the speed of the electrons?
Sure.
You can?
Well, you're asking in practice how much can you, not that much. So yes, you can change the energy of the varying the magnetic fields and so forth.
I had thought that one of the last experiments that did SLAC was with polarized electrons.
Polarized electrons, yeah. It's hard to make polarized electrons, but once you make them, you can accelerate them. So the electrons are made in, slow electrons are made which are polarized. Don't ask me how they're polarized, I don't remember, but then they're accelerated as polarized electrons.
If you remember, it's a very low energy spin orbit interaction that selects a particular.
Yeah, but the details of how, I can't remember. It's not easy to do. You need big magnetic fields, and it took a while for them to generate the technology to do polarized electron beams.
Polarized means all the spins are in the same direction.
Yeah. Yeah.
So what about neutrinos then?
Okay, so neutrinos, all right, so in the standard model and in old time physics of the before recent years, it was not known whether the neutrino, it was thought that the neutrino was massless. Now the mass of the neutrino is very, very small. Remember, there are several different neutrinos, electron neutrinos, muon neutrinos, very small. Within experimental error, they move with the speed of light. And that means that it's possible for them to have only a single-handedness. Right? In a standard model, neutrinos all are left-handed. The standard model does not even contain anything that you could call right-handed neutrinos. Generalizations of the standard model have right-handed neutrinos, but those right-handed neutrinos typically have a very large mass, and it's a complicated story. Maybe we'll come to it. But in the simple standard model, neutrinos are massless. Now, do we know, are they really massless? They're not. We know they're not. We know they're not because of neutrino oscillations. So we know they're not, but their masses are very small, 10 to the minus 3 electron volts or even smaller. And approximately, they're very close to massless. They're not quite. What actually happens to the neutrino is really curious. Remember, a mass term is a thing which turns left-handed to right-handed. Right? So it's a process in which left-handed can make a transition to right-handed. Now, what happens with the neutrino? There are left-handed neutrinos, and of course they go along with right-handed antineutrinos. If a neutrino is left-handed, then the antineutrino is right-handed. And one way of having a mass for the neutrino is to have a left-handed neutrino make transitions to right-handed antineutrinos. Mass is always, for fermions, it's always left hand turns into right hand, turns into left hand, turns into right hand, processes which involve that. For neutrinos, curiously, the right-handed particle, which the neutrino can make a transition to, is the antiparticle of the left-handed neutrino. So that's an interesting fact. Why could the electron, the real electron, why could the real electron not get a mass by mixing by the left-handed electron with the right-handed positron? You'd be pretty amazed to see an electron turn into a positron because it violates charge conservation. So that's not an option for the electron. Why is it allowed for the neutrino? Has no charge. Has no charge. Right. The buzzword terminology for a particle which gets a mass from a Dirac equation, it's very curious. The thing on the right-hand side here is the antiparticle of the thing on the left-hand side for a neutrino. A particle which gets its mass by mixing in this way with its antiparticle is called a Majorana particle. Majorana. It was Majorana, the young Italian physicist, I'm not even sure what year, Majorana. Ettore Majorana, who disappeared shortly after inventing the Majorana particle and never was heard of again. I don't mean he wasn't academically heard of. I mean he was never heard of again. Nobody knows what happened to him.
The mafia doesn't like Are you going to be able to tell us why we think the Higgs particle is going to be reached, the mass of it will be?
Yeah, we can talk about, turns out the mass of the Higgs particle is also generated by the Higgs particle and is also ordered the same F. So we more or less expect that the Higgs particle will have the same order of magnitude mass as the W and Z boson. Somewhat heavier, but more or less the same. But, okay, so let's think about it now, what we found. This is somewhat striking. All masses in the standard model trace back to this parameter F. If F were 0, they would all be massless. All right? All the particles of the standard model, with the possible exception of the Higgs boson itself, but all the particles of the standard model, all the familiar guys, and even many of the unfamiliar ones, Z and W and so forth, top quarks, bottom quarks, the whole works, all of their masses are a response to this F. They're all proportional to F in the formulas of particle physics. Why is that? Why are there no particles in nature whose masses might not be much, much larger than F? Well, maybe there are particles which masses are much larger than F. We just haven't discovered them yet. Why not? Because the limits of our energies are roughly at about that level now. This number F, in order to agree with the masses of Z and W bosons, this number F, thought of as a mass, is about 250 GeV. If there were particles in nature whose mass were much larger than 200 GeV or so, we would not have discovered them. All right? Supposing there were particles, let me give you an example of a particle in this context, in this slightly fictitious but still qualitatively correct context, where a particle could get a mass that was not due to the Higgs boson. Suppose we had a particle in this weak interaction context where both the left-handed and the right-handed components both had the same charge with respect to these weak interactions. Suppose such a particle existed. Right? Then there would be no obstruction to having a mass which had nothing whatever to do with F. It could have a mass which would be arbitrarily big. It could be much, much bigger than F. It could be 10 to the 16th times bigger than, or even bigger than F. There would be no obstruction to it having a mass having nothing to do with this F. There are other kinds of particles that could have masses which are not due to this F. The thinking now is that the natural mass scale of elementary particle physics, wherever it comes from, we can talk about where it comes from, is much, much bigger than F. Any particle that can have a mass will have a mass, and that mass will be much, much bigger than F. It is only those particles for which there are symmetries, there are deep underlying reasons why, in the absence of spontaneous symmetry breaking, they can't have mass. The gauge bosons themselves, the photon is one of them. These particles which are purely left-handed, they are forbidden from having mass unless there's a spontaneous symmetry breaking. So maybe it's not so surprising that all the particles which have low enough energy to have been detected, all are the ones whose masses are coming from the same origin, namely a small amount of spontaneous symmetry breaking. All the other particles which could have masses independent of this F simply apparently have masses at some scale which is much larger. That's the thinking. So it's not, in that sense, the particle spectrum as we know it consists of the particles which would have been massless if the symmetry was not spontaneously broken. They're all responses to a small amount of spontaneous symmetry breaking. That's the thinking in any case. This may or may not be true.
Does that mean that they don't play a large role in reality?
Well, it definitely could mean that. It depends, of course, on what you mean by reality.
If they can't produce their energy is too high, then
Which ones don't play a big role in reality?
these ones with the finite masses.
Oh, the ones which can have masses, they do not play much role in ordinary physics. Now, one exception is the possibility of dark matter. The best guesses about theories of dark matter is that the masses of them are significantly larger than this F, possibly by a factor of 10 larger than this F. For such particles, it's unreasonable for various reasons to think that they get their mass in this way. And so dark matter particles may be the first indication of a spectrum of particles whose masses do not come from spontaneous symmetry breaking. That's the thinking in general, or at least this particular spontaneous symmetry breaking. Yeah.
What is the mass of cosmic ray?
Well, it depends. Cosmic rays can be electrons, they can be protons, they can be photons. What their mass is the mass of those particles.
They're very high energy, right?
They're very high energy, but mass means energy at rest. Right. All right, so you could ask me, what is the energy of cosmic rays? Well, basically anything up to about 10 to the 21 electron volts. So 10 to the 21, what's 21 minus 9? 12. 21 minus 9 is 12. 10 to the 12th GeV, which is very, very high, higher than any accelerator that we're going to build. Incidentally, cosmic ray collisions, in a certain sense, will not be as high an energy probe as accelerator probes. And the reason is because the cosmic ray is banging into a particle at rest. The Hadron Collider will collide together two particles, and you may think of it as twice the energy, but it's much more potent than that. We can come to why. Hitting a particle at rest with a high energy is not typically as potent as hitting two particles head-on with a good deal lower energy. So what will be measured in CERN will be processes at energies, no, still not as high as the highest cosmic rays. Not quite, no.
One term that you don't use, or you use infrequently here, is inertia. Is inertia and mass essentially the same thing?
Yeah, well, yes. Yes, and now you can ask, by what magic is it that inertia and these expressions in Dirac equations and so forth correspond to the same physical idea, and that's more complicated. But you could go back to basic relativity, and you could have asked special relativity, and you could have asked the same question there. Two different definitions of mass. One of them is inertia, all right, how hard it is to get a thing accelerating, and the other is energy at rest. Why is the energy of an object at rest related to the inertia of how hard it is to accelerate it? All right. That is contained in the rules of special relativity, but once you know that, then you might as well focus on the definition of mass as energy at rest. Right. So the question does not have to do with particle physics. It doesn't have to do it. It has to do with special relativity. Yeah.
So once it obtains mass, does it start to couple with the gravity field?
Exactly. Well, it couples. Yeah. Yes. That's right. Good. So that's correct. Once it gets mass, it starts to couple to the gravity field. Now that's a little bit. Not quite accurate. Photons don't have mass. Photons do couple to the gravity field. What is it about photons what is it that really couples to the gravity field? It's energy. Energy. Energy is the thing which really couples to the gravitational field. How do we know that photons couple to the gravitational field? They bend the trajectories of a photon or deflected in a gravitational field. Action equals reaction, and so that means that the orbit of the sun is slightly perturbed every time a photon goes past it, but that's pretty negligible. But just the fact that, that photons are deflected when they go around the sun means that, that massless particles do couple to gravity. But particles at rest, their energy is simply their mass. So if you have two particles more or less at rest, the gravitational interaction between them is related to their mass.
Well, resistance to acceleration is also related.
What's that?
Resistance to acceleration is also related to total mass.
It's related
To energy, not just to energy, not just to energy.
Indeed it is. Indeed it is. That's correct. The resistance to acceleration of a high energy particle is bigger than the particle at rest. Yeah. The only subtlety is that let's call it the resistance to acceleration. If a particle is moving down the z-axis, then there's a different effective inertia of it if you make a force along the z-axis or if you make a force perpendicular to the z-axis. So there's no universal concept of mass, unique mass, for a particle which is moving. Depends on which way you push it, what its inertia is. That's why people stopped talking about the mass of moving particles, which mass, and stopped talking about that and defined mass to be the energy of a thing at rest. But yes, it is correct that the more energetic an object is, the harder it is to deflect.
How do you know if an electron at rest is left-handed or right-handed?
Well, in a certain sense, it's not left-handed or right-handed. An electron at rest, the handedness is the relationship between the momentum, and it's particularly well defined for high momentum. For high momentum, the definition of a right-handed particle is one whose spin is along its momentum, and a left-handed particle is one whose spin is opposite. So the answer is that there is no definition of right-handed and left-handed for a particle at rest. It's mostly useful for high-energy particles, the notion of handedness.
Yeah, but if an electron is at rest, can it not interact, have a weak interaction? Or?
Okay, this now you've really pushed me to the edge of, okay, so. All right. There's a subtlety which I haven't told you about, and it's the difference between what is called chirality and helicity, and I promised to tell you about it. I've been a little bit loose in what I mean by handedness, so let's come back to it. The idea of handedness, as I've defined it, is especially useful for high-energy particles, particles whose momentum is very large. When the particle has a very small momentum, the handedness of it is oh God, I'm losing my it's getting too late for this. We'll come back to it. Yeah, I will explain it to you.
Just quickly say that the Higgs boson should be in the order of 250 GeV in mass.
No, F is of order 250 GeV. The Higgs particle, there's good evidence that it's a good deal lighter than that.
Yeah, what evidence is that? Is the question.
High precision experimental and theoretical comparison between the properties, the masses of the Z and W bosons. They would respond to changes in the mass of the Higgs boson in a certain way, and from experimental knowledge of the masses of the Z and W boson, I would say the bound on the Higgs mass is probably that it's less than 160 GeV. So that's less than this 250 GeV, but not by an order of magnitude.
So I want to follow up on a question I asked earlier about the possibility of multiple minima. Mm-hmm. And it occurs to me that if you had particles which you didn't see in generations, then that would get in the way of having multiple minima in that potential function so you'd have multiple f values from one potential function.
Yeah.
So if you had a particle that didn't exhibit generations, then it wouldn't make sense.
Let's come back to it. We will talk maybe next quarter a great deal about multiple minima and what kind of different physics can take place in different minima. But simply stated, you can have anything happen, almost anything happen in another minimum of the potential. So I didn't want to get into that tonight. I'm getting tired, as you can see. So ask me some more questions. If the energy level that's required to answer them is low, I will do it.
We're going to have a class next week.
What's next week?
Next Monday. I mean, are we at the end of this course, or are we going to have another class next week?
What's the date?
Ninth.
This is the 9th lecture. Well, then I suppose we have another class. I know I have to be away at some point, but I don't think that's till the 18th. Oh, yeah. Yeah. Well, we don't have to have 2 classes, and we won't have 2 classes because I'll be away for the 11th week. But for the 10th week, which? Yeah, let's meet. Why not? Sure. Okay.
That's where we'll have it next week?
Yeah, if I recover from tonight. Yeah. There are various scenarios for the value of the Higgs boson mass, and in some of them, the range of energies is quite is easy. It's the rate and the things that things decay into. Sometimes they decay into just invisible things. So the Higgs boson will not be the first thing discovered at LHC. Of course, it may be the first thing discovered if nothing else is discovered, but there's a lot of room for discovery before the Higgs boson, particularly if there's supersymmetry.
The photon and the gluon don't seem to have antiparticles. Is that because they have 0 mass?
No, it does not have to do with their mass. It has to do with their absence of having any kind of charge to distinguish the particle from the antiparticle. So the photon is uncharged with respect to any kind of charge that we know about. It doesn't participate in weak interactions. It's not electrically charged.
Neutrinos have no charge, and they have any particles.
Say it again?
Neutrinos have no charge, they have any particles.
They must have weak charge. Anti-neutrino.
Yeah. They also don't have any conserved charges.
But there are anti-neutrinos.
There are that's, well, are there antineutrinos? Well, no. Some people would say there's only one kind of neutrino and it's both left-handed and right-handed. Other people would say there are neutrinos and antineutrinos. The point is the neutrinos can mix together with the antineutrinos and form a massive Majorana particle, which is its own antiparticle. Why? Because it's a superposition of a particle and an antiparticle. So it's, there's some subtle quantum mechanics there.
Does the standard model try to explain why charge is quantized?
No. Well, yeah, we can talk about that too. It does. But only, it does. Remember that neutrinos have weak charges. They interact under the weak interactions. And so the weak interactions provide this collection of charges that we've been discussing, and the neutrino is not uncharged with respect to the weak interaction, with respect to the Z and the W boson. In particular, the neutrino and the antineutrino interact differently with a Z boson. So you might say that with respect to a Z boson, the neutrino and antineutrino have opposite charge.
You can have pair production of an electron
They also have lepton number, which is another conserved quantity.
Right, but I was going to mention that. If you can have pair production of electron and neutrino,
Yeah.
and they have to have the same, I mean,
Right.
conserve lepton.
Unless the lepton number is not conserved.
But anyway, they have to have opposite weak.
Okay, all right. I'm nodding my head yes, but I know deep in my heart that the answer is no. And the reason is that lepton number is not really thought to be conserved. Right. And it's connected with this Majorana story and the mass of neutrinos. Neutrino oscillations can mix neutrino with antineutrino and things like that, you know.
For more, please visit us at stanford.edu.